Advanced semiconductor manufacturing is hitting a hard physical limit at the molecular level. The transition to gate-all-around transistors and three-dimensional DRAM requires atomic layer deposition. This process relies on highly volatile organometallic precursors to build silicon layer by single-atom layer. Global demand for these high-purity precursors is scaling exponentially. Volume requirements are projected to reach 360 metric tons by 2026. This represents a 200% increase from 2019 levels. A structural supply deficit emerged in 2021 as chemical synthesis capacity failed to keep pace. By 2026, the market faces a projected 95 metric ton shortfall. This deficit is compounded by a severe logistics bottleneck. Specialized, temperature-controlled shipping cylinders now require 52 weeks to procure, up from just 8 weeks in 2019. The supply chain for these critical chemicals is highly consolidated. Over 72% of global 9N purity precursor synthesis occurs in South Korea and Japan. This geographic concentration creates an extreme single point of failure for global chip makers. Only 13 facilities worldwide are qualified to synthesize and purify these compounds to the required standard. This standard demands a purity of 99.9999999%. The United States is highly vulnerable, holding just an 8% share of global synthesis capacity. This entire domestic supply is concentrated in a single facility. Any localized disruption in East Asia would immediately halt advanced logic fabrication worldwide. Capital expenditure in domestic fabrication plants cannot bypass this geographic chemical bottleneck. The bottleneck is governed by unforgiving laws of materials science. At sub-3 nanometer geometries, trace metal impurities exceeding 100 parts per trillion degrade gate dielectric breakdown voltage by over 26%. This drops the breakdown voltage from 12.4 to 9.1 megavolts per centimeter. Consequently, achieving 9N purity is a non-negotiable requirement for advanced fabrication. Allowing impurities to rise to just 100 parts per trillion causes average wafer yields to plummet from 94.2% to 68.5%. This yield drop renders high-volume manufacturing economically unviable. Purification requires multi-stage fractional sublimation and vacuum distillation. As purity targets scale from 6N to 10N, production throughput decreases exponentially, locking the industry into a high-cost, low-yield chemical processing bottleneck.